The Secret of Flight, a series of programs on aerodynamics. Program 8, The Induced Drag. Your host is Dr. Alexander Lippisch.
In our last program, we talked about the aerodynamic drag, the air resistance. But the air resistance actually is not the only thing which you have to overcome with the power which you build into an aircraft. See, you also need power to make the lift. Two types of power you need. Power to overcome the air resistance, just to make it moving forward, and power to produce a lift. This is a difference between a land vehicle, like a car, or let's say a train, and an airplane. With the car or train, you need the power only to make the thing moving, to overcome the friction towards the ground and internal friction and things like this. And the weight is supported by the solid ground. But with an airplane, it's different, because when you fly through fluid matter, through air which can yield away. And in this way, you have to bring all the time new masses of air into play to be supported by a downward motion of these masses which continually come into the vicinity of your aircraft. You could probably compare this with a very simple example of a man who wants to cross a pond on some logs which are swimming in the pond. And let's assume that these logs are not large enough so that he could just stand on one of these logs. Now, if you think of this, we might sketch it just up. Then you have here, for instance, the beach on the one side, and then there are the logs in the water, somewhere around here. So, and on this other side is the other beach. Now this fellow wants to run over it. And while he runs over it, the logs give way. So actually the picture which you would make while he is running shows that the logs he just touched and is supported by them are underneath the water line. And the next one he just begins to jump on is beginning to sink, while another one he has just left comes slowly up. And here is this fellow now, which we might sketch in the simple way, standing up there or running up there from this to this. So actually the line of the logs, if you connect all the centers of the logs, is a curved line. And this fellow has to run all the time uphill, because the logs gave way. So the log on which he is standing is lower than the ones where he wants to get at. And he has to get up all the time uphill. So even if this whole motion would have no friction, he would still have to do work, because he has to work uphill. And this is the same with an aircraft, because also the air gives way, and therefore when you have an aircraft flying here, let's sketch it up, might be this would be some kind of an aircraft. So then the air which supports this aircraft is in a downward motion on the spot where the aircraft at the present time is. And this aircraft, instead of flying in air which comes direct against it, has to fly in air which comes above. So that even if you think of this being so smooth that there wouldn't be any friction, you still have to work, because you have to fly actually against air uphill. And in this way, you have to do work. Now, this is a general concept of what would happen and why you have to do work to produce lift. But if you look at this process a little bit more specifically, that means look at the wing itself and at the motion what would be around the wing, the motion of the air, well, then you must say, where does the air yield away? Now let's look at the aircraft, let's say from in front. Here's the fuselage. So now since this aircraft is supported by the air, you must have a pressure differential across the wings. So underneath of the wings, you have apparently positive pressure, as we have seen it in this tunnel, and we have demonstrated it. And above the thing, you have negative pressure. And this pressure differential supports you because pressure underneath, suction above, gives the lift. But what happens on the wing tips, on the corners, on the edges? Well, there a mass of high pressure air meets a mass of low pressure air. And since plus goes to minus, the higher pressure air wants to flow towards the region of lower pressure air. This floats around the tip, and this floats around the tip. And while you are now in forward motion and have this motion around the tip, the resulting motion of these air particles is what? A spiral. And if you look at this from in front, you are flying this way, let's say, then you would have here a motion of the air which comes around and goes backwards, and this backwards motion gives you what we call, well, what do we call it? A vortex. And these vortices are originated on the wing tips of the aircraft, and they produce this downward motion of the air we talked about before. But even if we probably go a little bit more deeper in this problem, we like to see it at least in the smoke tunnel. And I have here a model of a wing. You see, this is a plain straight wing. These are the two tips. And I put it in this way. And I have here a gadget so that I can change the angle of attack with these controls. Now let's put this thing in there. You will then observe one thing. Well, as long as we have no lift, we wouldn't have any pressure differential, because then pressure on both sides of the wing is the same. So result is that we wouldn't have any of these curls on the side, these wingtip vortices. If we have more lift, we get vortices. The moment we increase lift, the vortices must get stronger and stronger. And this we might see here pretty good. Now let's adjust this model. You see, I have here two handles. The one is used to put the thing straight, and the other one is used to give an angle of attack. An angle of attack is this one here. Now let's put it, if we have now smoke, then we can probably see it. There it begins. Now let's put it first at an angle of attack where we have no vortex or no lift. That's this position, for instance. You see, the wake behind this wing is mainly due to the friction on the wing surface. We get then resistance. Now we change the angle of attack to a larger angle. That means we make lift, and there are the vortices. You see them very nicely. And even to see it better, we have another model, only the model of a wing tip. That means an enlarged piece of, let's say, this wing tip. And we can can put it down into the tunnel now in this way and can see the formation of the vortex even more definitely. This model we put now in the tunnel, this wingtip, is actually only half as wide as the tunnel itself is. In this way, we see kind of a three-dimensional development of the vortex in this small tunnel. Now I think the thing is in there, and we have adjusted it so that we have no lift. You see, then we have a little negative angle of attack. Now if I increase the lift, excuse me, it takes a little time there. Then you see at once how this vortex develops. You see very clear these curls, these spirals, beginning here while the flow goes from the lower surface to the upper surface. Here underneath we have pressure. Above we have suction. And the air flows from the pressure side to the suction side. Now it is carried away, and due to this rotation and translation, we get this vortex. It's interesting to see that this is not a motion which causes friction, because these lines stay very well together. That means it's a completely frictionless flow around the thing. But due to the production, to the generation of the vortex, you need a certain amount of energy. You see, you cannot produce just a vortex for nothing. You put this rotation into the air, and the amount of rotation takes away a certain amount of energy, which you have to counteract with the power in your aircraft. Now, when we put this in negative angle position, you see, go through the zero lift and go to the other side, then you see that the vortex starts the other way, because now we have pressure above and suction below. You might think that what we see here in this pretty small, more or less two-dimensional tunnel is only a kind of a visualization, but it might not be completely true. But we have therefore made some pictures in our three-dimensional tunnel. That means a tunnel which is so wide that you can put at least half a wing in it. I think you remember I told you once that this tunnel has a rectangular cross-section, and we fasten the wing on one side, so we see half of a wing, and the vortex develops then on this wing tip. And we have made several pictures where you can see them. Here are now the films. First, a picture where we see where the smoke comes out, and we begin with no speed at all. Excuse me. The moment we blow, the moment you see that the flow which came out underneath starts around the wing tip and flows to the top and forms behind this wing a vortex. Here we have, for instance, a condition where we have no lift. Now we increase the angle of attack, and at once the rotational motion around the tip starts, and you see very distinct these particular flow lines, which now spool up all into kind of a rope, which forms this vortex, which starts from the upper part of the wing tip. We have then a picture where you can see this from above, so that you can observe that the core of the wingtip doesn't start just at the corner of the wing, but more or less at this edge where the upper surface of the wing ends, and it is a little bit set inside, so that the distance between the cores of these two wingtips is not the two span, but it is a little smaller than the span. This causes a certain loss of energy, because then the vortices are even stronger. With particular changes and particular forms of the wingtips, you try to improve this. Here we have the picture from above. But we see it even better if we can look at a film which is taken in the same tunnel just from behind, so that we observe the rotation more clearly, and then we can do it here. There it is. And we have released also some smoke from the leading edge to show you that not only the air masses which are just around the tip produce this rotational motion, but that also other masses of the air which are in between the two vortices take part in this rotation. The core of the tip vortex is in some pictures to see as a fine dark line. Actually, these vortices are very stable and stay there for a long time. So if some airplane has flown over a certain region and it has left this place, the tip vortices which he has produced will still stay there. Here is a very nice picture direct along the core of the vortex, where you see very well this rotational motion. Again, a picture from the side view where we see the single flow line, and we observe one thing, that the slope of the line increases towards the rear, because this rotation is caused by the lift. Now, the front part has not all the lift, but until you get to the rear end, you have assembled all the pressure differential which is there, and therefore the spiral gets steeper and steeper towards the rear. Now, we might think how this vortex motion ties in with what we talked before, that the air is moving downward even at the point where the aircraft flies. You see, when we have here the wing and these vortices on both sides, they induce a downward motion behind the wing. But when you see it from the side and you have here this vortex and here this vortex, this motion, this downward motion is even beginning before the wing is at this point, so that when you look at it from the side view, there is a downward motion of the air at the point where the wing is. And in this way we have to go uphill actually all the time, and the work which we need to produce lift is the work which is necessary to go in this uphill direction. Now you think, what could you do to reduce this? Well, let's think about it. We have, as we said, underneath the wing, the higher pressure, above the wing, the lower pressure. If we would distribute the load on the wing over a larger distance, a larger span, we call this distance from one tip to the other tip the span of the wing, then certainly the pressure differential across a certain section will be smaller. And therefore, when this pressure differential from below to above is smaller, then also this rotation is smaller, and we get smaller tip vortices. And that is the reason why, for a highly economical aircraft, we should have wings which extend into large span. And since we cannot increase the surface of the wing, otherwise we would get too much surface friction, we have to have a very slender wing with a small chord, the chord length we call from the leading edge to the trailing edge, and a large span. And this ratio between the span and the mean chord of the wing, we call it the aspect ratio of the wing. You might hear it very often when people talk about it, aspect ratio. And you see that aircraft for high flight economy have high aspect ratio. All these laws of the vortex motion and the vortex formation on the wings were discovered originally by Lanchester, and the theory about this whole problem was mainly worked out by Prandtl in Göttingen. It was first applied on gliders, and I have here a picture of a high-performance glider we did long time ago, where you see very well that we have a very small chord and a large span. Actually, this aspect ratio of this particular high-performance glider was 20:1. That means the chord, the mean chord of this wing, is 1/20th of the span. And if you look at a modern transport aircraft, at an airliner, you will see that such an airliner has again a very slender long wing and uses the main basic principle of high flight economy in generating lift, as we did it once on the high performance gliders. Now, you could do that, not all the time. You couldn't build a very slender wing because, well, you must think that when you fly, you have to suspend the weight. And when you build a very slender wing, then you have to have a very heavy structure within the wing to keep it from bending too much. And therefore, there is a certain technical limit in having wings with high aspect ratio. And you sometimes think of methods to make this process more efficient with normal sized wings, especially if you come into the high-speed flight condition where you cannot afford to make long, slender wings at all due to other laws which are connected with the high-speed and supersonic flight. And there you see, for instance, an application which you can observe very often on jet aircraft, on high-speed aircraft, where you see that on a wing which has a normal span, we placed out there two streamlined bodies which now are used as tanks, so-called wingtip tanks, or for housing radar equipment, anything like this. This has a meaning that when you put such a rounding on the tip, then this motion around the tip will be more smooth. And you actually can, in this way, improve the flight efficiency of such aircraft. We have made a picture of such a wingtip tank on a normal wing in our tunnel, and you will see it here. Now, what we learned today is this. The formation of the wingtip vortices causes a downdraft on the wing itself, and in this way needs power to climb all the time against an air mass which is in the downward motion. This downward motion is induced direct by the aircraft itself. And therefore we need power to generate the lift. Actually, it is so that in cruising flight, 50% of the power is needed to overcome the air resistance, the friction drag and some turbulence. And 50% of the power is needed to generate the lift. In our next program, we want to talk about the development of the aircraft type of the original biplane to the latest types of aircraft as we have it, for instance, with swept wings. As you see here, a model of it, which we just put shortly in the tunnel so that you might observe also the flow around such a wing. Now my assistants have mounted this swept wing model in the tunnel, and if I turn the light on, we can see very well the flow around such a wing, where you also see the formation of the tip vortices. But let's talk about this in our next program, where we will explain the development of the aircraft configuration from the biplane up to the latest types, the delta wings for the supersonic flight. Up to this time, goodbye and auf Wiedersehen.
You have just seen the induced drag, the 8th in a series of programs explaining the secret of flight. Your host has been Dr. Alexander Lippisch, Director of the Aeronautical Research Laboratories of the Collins Radio Company. This program was produced for the Educational Television and Radio Center by the State University of Iowa.